But it's a pleasure to introduce Chinmay Nirkhe, who did his PhD with Gumesh Bazarani at Berkeley, just finished it in 2022, and is now a research staff member at IBM Research, where he's doing research in quantum computation. Chinmay is one of the people really pushing the forefront of quantum complexity theory, and in particular thinking about versions, or trying to get towards something called the quantum PCP theorem. So one of the most important and deepest theorems in theoretical computer science is something called the PCP theorem. I'm sure he'll tell us about it. It's a big open question whether something analogous exists in the quantum realm. And it's a deep question about entanglement, about complexity, potentially about approximation algorithms and other things. And I think he's going to introduce those ideas and give us a status report.
Okay, thank you. Well, thanks for a wonderful introduction. So my goal today is to talk a little broadly about how to classically describe quantum systems. So that'll be sort of the center, what I'll talk about. I'll say a little bit about quantum computation and how it sort of gives you a way of describing quantum objects. Talk a little bit about local Hamiltonians, a little bit about entanglement warm temperatures, and the last thing is that the way we'll sort of understand description complexity and sort of maybe more physics notions is through a more mathematical or computer science notion of circuit lower bounds. Okay, well, to start, why do we believe that quantum systems are exponentially complex? Maybe the easiest way to think about this is like what gives the complexity of quantum systems is to think about a very simple example. Think about a bell pair, right? Two particles entangled. You could write it down as this vector over 4 dimensions, and you contrast it with the classical system. And what do you notice? Well, you notice 2 things. One is that you can't really describe this quantum system by describing the first particle and then the second particle, and that's because of this entanglement, right? That somehow the description of the state doesn't suffice to describe each particle one at a time. Any holistic description that's faithful to the entire system has to describe the correlations, right? So when the first particle by itself just looks like a random coin, but the real key is that it's entangled with the other coins. So whenever the first one's head, the other one's heads and tails, and in fact, this is true in all bases. So at a high level, if you leave with one thing, I think the way I think about quantum entanglement is it just means that it doesn't suffice to describe each individual particle. Entanglement is coming from sort of the correlations. And then you say, okay, well, that's 2 examples, there's 2 particles, what about n particles? Well, okay, so it's an n particle system, and then you say, well, the only reasonable way of writing it down is this 2 to the n dimensional vector, right? You describe all the possible positions that the n particles could be in. So here I'm just going to assume particles are qubits. For higher qubits and stuff, you can make an analogous statement. But it says, okay, well, this is the only possible explanation. That hits you with the fundamental problem, right? Hits you with the fundamental problem that the space of n particles is just too big. N equals 500 and stuff. It says, well, there's no way you're going to be able to describe the state of the system classically. But it misses the point. It misses something fundamental, which is that why did we even believe that this was the best representation? It's totally possible that it's a faithful representation, but it's a priori not clear that it's the best representation of the state. This isn't like a fancy new idea. It's actually something very old. Like most people know of, Caltech's famous speech Feynman's famous speech at Caltech, saying that, hey, if you want to simulate quantum mechanics, you have this fundamental exponential distribution. So the only way to sort of faithfully simulate quantum mechanics is to do something quantum, right? That you need quantum to simulate quantum mechanics. And that was actually only half of what he said. People always, with good quotes, there's always a part where someone always skips the important second half. The second half he said was actually that, well, maybe this was the wrong explanation. Maybe there's a simpler, much easier to write down representation of all quantum states, and you don't necessarily need a quantum system to simulate quantum mechanics. And in some sense, this is the answer we get when we think about the fact that there are a lot of systems that behave quantum mechanically, but that even with pencil and paper, we can understand their mechanics and understand just by calculus and these kind of techniques something non-trivial about them, despite there being a true representation that might be this exponentially large vector space. So it suggests that within the space of n particle states, nature could sit in any one of these configurations, but in reality, there's a much more minuscule physically relevant corner. And that physically relevant corner has a stronger notion of tractability. So we're able to sort of manipulate it a little better. So what could we mean by a physically relevant corner? Well, let's go back to, what are the things we want to represent? And the things we want to represent might be the solutions to physical systems. So we might be considering a Hamiltonian where you sort of have local interactions. And, each local interaction for a Hamiltonian is just a small matrix. This describes not only the evolution of the system, but also the energy of certain configuration, right? And each Hamiltonian that describes a local interaction as a succinct representation. So if these two particles were just isolated and we wanted to understand their dynamics, that's really easy to do on our classical device because the dynamics are only described by a very small matrix, a 4x4 matrix. And you might just be able to solve any Schrodinger equation with them, pencil and paper, or at the worst, like a graphing calculator, right? Okay. And, what are some examples? Well, you could have a Hamiltonian that prefers quantum states that are both spin up or both spin down, right? So I'm a computer scientist, so this is a simplification of but it's a start that a computer scientist can think for this. And that Hamiltonian is a very simple matrix; it's a diagonal matrix. So this actually describes sort of whenever the interactions are classical. Whenever the interactions are classical, we end up with diagonal matrices. But you can have more complex interactions than that. You could have interaction that favors the bell pair. The stable space of the two-particle interaction is to look like a bell pair, and that Hamiltonian is naturally more complex and certainly non-diagonal because it sort of enforces a quantum interaction. And okay, a priori, what happens is, if you have Hamiltonian interactions that you can understand each of the particle pairs by themselves, well, what's the problem? Well, the problem is putting them all together. So in the previous example, when we had, these Hamiltonians, sort of like, they look kind of like they all either point up or they all point down. If this was the Hamiltonian interaction across the entire grid, the solutions are pretty easy to write down. They're just all up or all down, right? That becomes far less clear when you have these sort of more complex interactions. The issue sort of just becomes that we don't know how to stitch together a global solution given the local solutions to the problem. All right, okay. So, so now we want to sort of understand what are the global solutions. So you can say, okay, well, the local interaction is described by a 4x4 matrix. That's easy enough. But how do I think about that interaction globally? Well, mathematically, we could say there's a tensor product structure. So if we keep to this idea that the state of the system is described by this very long 2 to the n by 2 to the n vector, the matrix that is the tensor product with identity of whatever this local operator was, that describes that energy interaction between these two particles, but extended to be thought of as an interaction among all n particles. Okay, so now we can say that this interaction, we can view it as an interaction on all n particles, and then the only thing is, I need to add up all the interactions, right? There's this blue interaction, there's this red interaction, there's other interactions, and the whole collection of interactions all together describes the state. Okay, well, what are the good things? Well, this matrix here is huge. It's 2 to the n by 2 to the n. It's exponential. Nothing else you can do about that. But it has a very succinct representation this way, right? By just remembering where it came from, it can be easily described. So you get that the Hamiltonian has short descriptions. And then you might say, okay, well, Chinmay, all you're talking about is the interaction system. Well, initially, you were talking about states and how complicated states are. This is just this is sort of the system. This is the game, the rules of the game. You might say, okay, well, okay, so then what are the relevant states? The relevant states are those that are the low energy states of the Hamiltonian. And what is low energy? Okay, in this case, energy of a state is simply just the eigenvalue of the state when corresponding with this matrix. So it's just the quadratic form, which would be VHV, right? And low energy morally just means small eigenvalue. So what we want to do is we want to calculate what these low energy states are, what sort of the global solutions might be now that we've put together all the interactions. And so going back to this picture, okay, there's this physically relevant corner. Maybe we should just simplify and say, let's just think about low energy states of local Hamiltonians. Let's try to understand these states by themselves. And what does low mean? Well, you can take two notions. One is the ground state, that's the exact solution, right? This sort of generalizes a computer science notion of satisfiability, and that's one definition of low. But perhaps a far more interesting definition of low is the states of energy less than epsilon n. And why might this be? Well, as n grows really big, the energy of a state kind of comes to sort of represent notions of temperature. And indeed, this is sort of what the description of the state is at a constant temperature at a high level, right? Okay, so Hamiltonians, short descriptions, ground states, low energy states are the ones we want to understand. We should ask, are there short descriptions for the ground states themselves? And unfortunately, we actually know this one. This was proven by Kitaev in 1999 that it's QMA hard, the quantum analog of NP hardness. So it says it's not even computationally tractable to somehow describe the ground states of these systems. So that's out of the picture. But what about low energy states? Could any of those be easy to describe? So that's basically saying, okay, well, ground states out of the picture. What about approximations? How easy is this to describe approximations of quantum systems? And there's been a lot of work showing that in certain situations, the approximations to quantum systems are easy to describe. Probably the famous one is the one by Landau, Vazirani, and Vidic about describing the ground states of 1D gapped Hamiltonians. That's at this point in the talk, you could foray down that way, and you could say, what are the states which I really can describe exactly? Today, I want to go the other way. I want to say, let's talk about when low energy states are hard to describe. When you can sort of engineer quantum mechanics to generate things which require a lot of complexity. In some sense, try to engineer systems where the best description sort of starts to look a lot like the really tall vector. So sort of say, yeah, there might have been a better description, but we really don't think that's the case. Okay, so what am I going to say today? I'm not going to go into any proofs today. I think I'd rather stay much more high level and talk very broadly about ideas. And I'm going to talk about two conjectures that come from computer science, precisely that sort of target the description complexity. And I'll say a little bit about how we get to the first conjecture and how it's necessarily implied by the quantum PCD conjecture. So it's sort of this both a computer science lens and a physics lens on a very pertinent question. Then I'd like to say something about a new result of my own and Anna Narajan, which is proving even better lower bounds. But while the lower bounds that I'll talk about in the first case are sort of what are called unconditional, they're true as is. We don't need to prove some predicate conjecture. We can show here under some conjectured setting even stronger lower bounds. And then I'd like to say something which is probably a little novel about something that there's actually just been a very recent flurry of papers on the archive about what's called state complexity. Okay, so let me go to this idea called the NLTS conjecture. It stands for the no low energy trivial states conjecture. Okay, and to back up, let me say something about where we got started. So I said at the very beginning that I wanted to understand how easy it is to describe quantum states. But there was a reason why we started with that, is that we believe there's some sort of nascent connection between description length and entanglement structure. And this is something I told you on the first slide, right? That entanglement morally says that it's insufficient to describe individual particles, that in order to describe the system, you have to describe these kind of interactions. So, yeah.
Can I just ask one quick, maybe simple question?
Yeah.
I can write classically correlated states where it's not sufficient to describe the state of the individual objects.
Absolutely.
Is there a simple statement you can make about the distinction there?
Yeah, so any classical distribution you have on n particles, you can purify to think about a quantum system on 2n particles. And you could talk about the complexity of the state that is that purification.
But in words, I can assume that if I have two particles, either they're both up or they're both down.
Right.
Right?
Yeah.
So why is this exponentially worse than that?
Okay, so that's with two particles. And now with three particles, you could say they're all up or all down, and that's one option. But there are 8 different configurations of
Mhm.
3 particles, and the distribution might not be necessarily all up or all down. It could be that it's an equal probability of being states 1, 3, and 7, say, which could be 1 could be down, down, up, 3 could be down, up, up, stuff like that. So the more particles there are, it might be harder and harder to describe the vector, right?
That's even true classically, right?
Yes.
There are 2 to the n options there.
There are, yeah.
So why is this worse than that?
So there's a distinction between classical but randomized objects and classical but deterministic objects. So we're comparing to the deterministic object case here. So deterministically, solutions to systems, you can write down just as by describing each of the particles by themselves, right? And morally, so this is a much more technical answer, but if you have a distribution which is a satisfying solution to a classical system, then turns out that there must exist some element in the support of that distribution which is just as good a solution all by itself. And that element in the support is now much easier to describe than the distribution. So in the classical setting, whenever you wanted to give me the answer, it was always easier to give me the answer of a fixed point in the support.
I see. So you're saying I don't have to do it as a superposition now. I can evolve the individual pieces separately.
Exactly. Morally, what that says is in the classical setting, there always exists a low energy solution that is also easy to describe, right? There can exist low energy solutions in the classical setting, which are hard to describe, but the beauty is that there always exists a low energy solution, which is easy to describe. Quantum setting, we're going to show that's not necessarily the case. Great question. Okay. So returning, so I believe there's some sort of connection between description length and entanglement structure, and really why we pursue the notion of description length in the first place. So the way to think about this is it says, hey, the longer the description of a quantum state, in some sense that's suggesting the more complex the entanglement. So you get that description length is a measure of entanglement complexity, except there's a catch, so here would be the question we might want to ask, which is, are there local Hamiltonians with no short descriptions of low energy states? This would be a question you really want to ask, except it's really hard to understand descriptions, right? There's lots of different ways to describe quantum systems. You could describe them as vectors. You could describe them by circuits that generate them. You could describe them as stabilizers, right? We know 1,001 different ways to describe them. So making a statement of this notion also is sort of vague. Yeah.
And for states where you don't mean just the eigenstates of the Hamiltonian, you just mean states for which the expectation value is
Exactly.
constant.
Yes. Exactly. So what I'm missing here is I'm missing something fundamental. I'm missing that descriptions might not even be useful. For example, the Hamiltonian H could take 500 bits to describe. Right? I could write it down on my classical computer and it would take up 500 bits, maybe 500 kilobytes, doesn't really matter, on my classical hard drive to describe. Now, the ground state of H can take 510 kilobytes to describe because the solution is the ground state of this is just add the words the ground state of and then describe H, right? That's a perfectly reasonable but incredibly tautological description. In fact, it's a useless description, right? Just saying the answer to the question is the answer to the question. It says nothing, right? So in some sense, we need to understand that not only are we talking about descriptions, but we're also talking about sort of useful descriptions. And for that, we need a notion of complexity. We need to say somehow that I can use this distribution to do something. And it turns out what I'll say in a bit is that the minimal notion of a description is that you can actually verify that the description is correct. So verifiability of a description is an important first property we might want of a distribution. So the tautological distribution, the tautological answer, great answer, but totally unverifiable. Okay, so let's come to this idea and let's sort of connect description length and computational complexity and sort of build this connection together. Okay, so luckily, probably everyone in this room sort of thinks, okay, quantum computation, we know how to describe in the circuit model. So this is a classical circuit, which just has bit flips and controlled bit flips. But if you introduce a quantum gate like Hadamard, what you get is that you can start off with an input, which is in product. So it can be described as just describing each of the particles by themselves. What you get is that the end output is no longer in product, right? It's an entangled state. And so, yeah, one way you could think about quantum computation is you can view it as an input-output function, switch the input, get out a different output, yada, yada, yada. But what I'd like to say is that actually, you can also use quantum computation as a measure of complexity. I can think of this as no longer just a transformation from inputs to outputs, but I can also think of this as a recipe for how to build the object over there, right? And now we are seeing a connection. The longer the circuit is, the more complex the description, right? It's harder to write down, it takes more time. But also this connects to the notion of verifiability, that we still always have a verifiable description. Because at the end of the day, you have this sort of recipe that's building the object. So we can formalize this and we can say, okay, well, for any state, we can say the depth of the state is the minimum depth over the circuit which outputs the state, starting from all zeros. This is a definition. And why might this be a useful definition? Well, it gives you a yardstick. It gives you a yardstick with which you can understand the complexity of quantum states. So I'll divide it into 3 regions. The first region I call sort of the trivial depth region, which is any quantum state on n particles, which can be generated by a circuit of depth that scales linearly in log n. Now, why is this the right notion of trivial? Well, it's a notion of trivial because it turns out when you have a circuit of this short depth, there's an efficient classical algorithm for calculating the energy of the state with respect to any local Hamiltonian. So in particular, if someone came up to you and said, hey, here's this Hamiltonian, and here's the ground state, it's V. And V is so special that it actually can be described by a very short circuit. I can say, okay, well, I can just check that. Thanks for the answer, but let me verify it's correct. And I could do this on my laptop. There's a second version.
Hamiltonian in any dimension, it's just.
As long as the Hamiltonian is local, absolutely, yeah. So they could just tell me here's a state, and I can verify this property. It doesn't really matter as long as the Hamiltonian is local. The second regime is, okay, well, someone comes up to me and says, okay, I have the solution to your problem, but you're not going to like it. It's a state of polynomial density. Okay, well, luckily I work for a big tech company now. I can run my efficient quantum algorithm for calculating the energy with my quantum state, with my quantum computer. And the third,
just to make sure I understand, when you say the energy, you don't mean the expected energy, you mean the eigenvalue, verifying that it's an eigenvalue of H.
I just mean energy as the inner product quadratic form VHV, whatever that is. And V is going to be a vector of norm 1, so this is sort of a generalization of an eigenvalue, right? Okay, great. Yeah. Great. And then the third option is, someone tells me, okay, well, the state actually is past this. You can't generate with polynomial depth. It sits somewhere here. Well, mathematically, we know that there's a limit actually to what the depth of the state is. It's like 2 to the order n. Any quantum entanglement could be generated by a circuit of this state. But okay, in that case, I'm a little hopeless. So you get sort of 3 regions. You get a classical, a tractable quantum, and an intractable quantum region for quantum states. And so we right now sort of can do stuff here because, well, we have laptops, and hopefully in a couple of years we'll get to this thing. But there's a reality, which is that most states we'll never get to. And just like that first drawing I had, I really should bring it back up, which is that there's this physically relevant corner within the large Hilbert space. We're sort of seeing that phenomenon again, that, quantum mechanics says there's all these states. There's 2, they can be described, all the vectors that can be described over a dimension of 2 to the n. But what we see, right, just by some simple counting argument, is that most of those vectors are completely unattainable. Physically realizing them on our devices is just sort of a useless idea. Okay, but what we get is that, at least let me convince you that, now we have a measure of complexity that's also somehow tied to description length, right? So it becomes harder to describe because the description just gets longer as we go this way, but it's also fundamentally connected to like a notion of verifiability. So when we come back to this motivating question of understanding description length, entanglement structure, and computational complexity, we had this question, okay, can we describe local Hamiltonians with no short descriptions?
Excuse me?
Yeah.
So on the previous slide, there's an efficient classical algorithm for log depth. How do we see that? What is the algorithm? And why is it log depth is the right quantity?
Okay, absolutely. So let me address something that I should have said a second ago, which is that I'm thinking of quantum circuits with all-to-all connectivity. Okay, so in any row of the circuit, I can connect any two of the qubits. Why is that the right notion? Well, that's the right notion because that's actually very easy to classically describe and simulate. So we're going to talk about all-to-all connectivity. The idea of log n depth is twofold. One log comes from the fact that if you ever want to naively calculate classically some quantum computation, there's an exponential factor there. So that addresses one of the two logs. Okay, the real question is, what about the second log? Well, the second log comes from the fact that whenever the circuit is really short depth, measuring the energy of an observable. So let's say you have an observable that acts on qubits just 5 and 6, like a local Hamiltonian term that acts on qubits 5 and 6. The fact is, if the depth of the circuit is t, I can take that operator and I can evolve that operator via the circuit that describes the state to now be an operator that acts on the initial state, on the all zero state. The evolved operator will be at size at most 2 to the t. So when you evolve an operator by a quantum circuit of short depth, it only scales by like 2 to the t. So that's where that second logarithmic factor comes in. And then the two logarithmic factors together give you this log n depth triviality. Yeah, no?
I have a question to be convinced about this argument about this measure of complexity.
Mhm.
So like, how do we know that like our model of a quantum computer is the right model in the same way that like Feynman saying that the state vector representations may not be correct? My question is like, do we know of any like physical states that are in that red zone or that can be created in that red zone from like a trivial or commonplace physical interaction, but that we know would take a very long circuit to generate? And like,
Right. So there has recently been a paper, I saw the talk at QIP this year, on exact circuit lower bounds for specific states that were exponential. So now you can there was this like explicit exponential complexity lower bound. But I think it was for time evolutionary states. I don't think it was for local Hamiltonian ground states. So we know of local Hamiltonians which have explicit ground states of log n. Under certain conjectures, we have them in here, but it's not exactly the. Yeah.
How do I compare the all-to-all connectivity of the circuit and the locality of the Hamiltonian? Are they related or are they chosen separately?
So the locality of the Hamiltonian is just like as long as it just acts on a constant number of particles in this tensor product basis.
Just so that when you do this like reverse evolution, it's not supported on too much.
Right. So if the original Hamiltonian is k local, the reverse evolution gives you a k times 2 to the t size. Yeah. Okay, let me address something Noah said though that I think is worth, which is that here's this notion of description length that I want to bound short descriptions. This is an ansatz that I'm going to suggest next. That let's start to tackle this question of are there local Hamiltonians with no trivial depth of energy states? And why trivial depth? Well, trivial is exactly comes from this picture again. And so this is an assumption. It's fundamentally saying I want to prove something about short descriptions. In particular, I want to prove something about short verifiable descriptions. Unfortunately, even that class is not something malleable, right? Like trying to prove lower bounds for all short descriptions actually turns out to be quite a tenuous task. So we simplify and we first target a notion of trivial descriptions, trivial depth circuits. And turns out that even this is a subclass of all short verifiable descriptions. Proving this statement in yellow has actually turned out to be quite hard. So this.
So on your slide, you were relating this complexity notion to entanglement structures.
Yeah.
Are there actually notions of entanglement that can distinguish yellow and the
Short depth? Yeah.
No, if you go on to the next slide, sorry, or what were your words? The tractable quantum and the intractable quantum, because the entanglement entropy is saturated, right, by the time you
Get to like
get
log
to
down.
like, yeah, that.
Right. I mean, but entanglement entropy is only part of the picture, right? Like, and this is the sort of beautiful notion of like, how do you distinguish multi-partite entanglement versus bipartite entanglement? Like, bipartite entanglement, it suffices to talk about entropy, right? If you're just talking about entanglement between Alice and Bob, it's great, right? Multi-partite entanglement, it's even hard to sort of say what are the complex ones, because you know, entanglement entropy is not exactly the right picture.
Exactly. Are there entanglement measures that are known that can tell you the difference between yellow and red, or that keep growing as long as the complexity keeps growing?
I think the best one that we understand is just sort of circuit depth, but we don't really know other measures of entanglement for sort of many body entanglement. That's actually a great question. Is, you know, we should have a better metric. Short depth circuits is one metric, but it's not exactly the right metric, you know. But yeah.
Another, maybe I missed this. When you say short depth, this is with two body interactions?
Yeah, but it doesn't really matter up to constants. So this is a very computer science idea that, you know, if you talk about three body interactions, that's okay. It just there's always hiding a hidden constant, right?
But I'm not allowed to have gates that are the size of the system.
No,
That's the requirement.
no.
It can't be extensive.
Yeah, it can't be extensive. Yeah, no.
Are all of these definitions of depths defined with like a single gate set? So like a standard gate set that we're using?
So we can just allow, in this case, the gates to be the set of all 1 qubit and 2 qubit unitaries. So that's the most expressive gate set there is, and all the lower bounds will still hold. Yeah.
Why this question is so important? What possible applications could you have if we understand this?
Well, yeah. So let's get there. Why would you want to have this statement? Well, it's saying something that there's a system which is quantum at its ground state, and it's seemingly quantum at all its low energy states as well. So you could imagine that if you were actually physically able to construct this in a laboratory, that you would have a system which is truly quantum. Maybe the right way to say this is a robust notion. So as an experimental exercise, it could be something fundamentally interesting. But secondly, it's sort of saying that, you know, describing systems requires quantum mechanics. Because if you believe in the postulate of quantum mechanics, then you believe that these sort of systems could exist, and not only could they exist, but they're also like something physically reasonable. And hey, look, I don't seem to be able to really describe them using classical mechanics, even at constant temperature. Yeah. Okay, so this question, you know, it's not my own question. It actually was posed by Friedman and Hastings in 2014, which they actually said the same thing. Can they write down Hamiltonian systems where every low energy state required at least omega of log n? So this is just to get out of that trivial depth regime. And there was a lot of work on this, many different things. And at the heart of these were all computer science ideas that sort of went into play. And that's because the goal was to prove a circuit depth lower bound. And that's sort of a computer science notion, so that we used a lot of tools in computer science to prove this. The only problem was that through this collection of works, we were able to prove lower bounds on larger and larger sets of states, but the target of proving it for all low energy states was not satisfied. So we proved this last year, and yeah, why I think it's exciting is it says something about robust entanglement that can theoretically exist, even at some notion of warm temperature, right? And you know, let me be fair to say that, you know, here's theory, here's practice. It's a very far from what we could say practically, but it's sort of a mathematical exercise in, you know, what is possible, what could entanglement look like if we just think a little deeper about it. And let me say that this is some notion of engineering, right? It's a construction which you build from tools such as Hamiltonians, error correction, and expansion. This wasn't something that's like a natural Hamiltonian system that you'd find. It has to be some sort of there has to be some thought that gets put into it. So it's a little bit artistic. Yeah.
Actually, so related to that, in these series of results, is there anything known about if I have a d-local, geometrically, spatially local Hamiltonian, say RD, then this is not true, but you require maybe giving up these notions of geometric locality?
Yeah. So that brings up a good question. So one thing you can prove is this rigorous of a statement for all low energy states. You cannot prove in any constant dimensional lattice. That much is known. You're absolutely right. What you can show is that on a 2D lattice, on a torus, you can prove that every state of energy less than n to the 0.99, so n to the 0.99, not 0.99n, those states require this sort of log circuit depth. And that turns out to be tight for 2 dimensions, up to some constant factors. So yeah, so there are notions of NLTS for lattice geometry that are stronger, and those can also be studied, but with the caveat being you'll never be able to prove this for all low energy states. So not saying it's not interesting, it's saying that the question has to be artfully written down first. Okay, and there's something more, which is that this is actually not just entanglement that you might be interested in from the computer science side, from the physics side, but it actually connects to a notion from complexity theory called the quantum PCP conjecture, and I'll say a little bit about that first. Okay, so the classical PCP theorem was a statement about NP completeness. So you might know NP completeness. It says, well, if a verifier wants to learn something like, solve a traveling salesman problem, or he wants to color a graph, or, a variety of problems, which are something like, does there exist a solution that does blank? These sort of non-deterministic questions, you could always convert it to a notion of sending a 3-sat formula from a verifier to a prover, and the prover sends you back the assignment. Okay, but the catch being that in that case, the verifier has to now check the entire assignment. It's to check the entire proof to make sure it's actually correct. He can't skip any part of it because the proof might have been very brittle. If you, gloss over it for a second, you miss a error, suddenly it looks right, but the entire thing seems wrong at the end. Okay, but along came an idea that was fundamentally changed how we thought about computer science, which said, okay, in fact, you actually, instead of taking your NP problem and writing down as a generic formula, there's a structured subfamily of formulas such that the verifier does not have to read the entire proof. He can just read a few of the bits randomly. So he picks a few bits randomly, and he just checks if the proof is correct in those few spots. And if that's the case, then he's bada bing, bada boom, he's done. And this notion of proof checking was connected to a notion of satisfiability, which said that actually this comes from this idea that not only is it NP complete to exactly calculate how satisfiable a formula is, even calculating it approximately, even to estimate it is hard. So what is the quantum analog? Well, I said earlier that it was QMA hard to sort of talk about ground states of Hamiltonians, the exact solutions, right? Turns out that comes up again here. So you get this class QMA, which is the quantum analog of NP, and now the verifier asks the prover, whenever he wants to ask about something quantum non-deterministic, he says, hey, just tell me about this Hamiltonian and convince me of the ground energy. And so what does the prover do? He sends the ground state over. So the quantum PCP conjecture, and it's still a conjecture, it's been open since 2002, is that it's QMA complete. It's just as hard to estimate the ground energy up to 1% multiplicative error as it is to calculate the ground energy exactly. And so why send the ground state? Well, the verifier is allowed to be a quantum device here. So what the verifier does with this quantum computer is he just applies phase estimation and checks, hey, actually the energy was good. That's sort of that yellow regime of verifiability, right? You can verify stuff. You may not be able to construct the state, but at least you can verify it. Okay. So why might you care about this computer science statement? Is it sounds like adding the word quantum to a regular computer science statement, and there's a lot of papers in that regime, and a lot of them are not that useful. Well, let me say something that is actually saying something about the robust entanglement. So let's say, if the quantum PCP conjecture is true, prover might come along and he might decide to be a little lazy. He says, well, I didn't have to send you the ground state. Since you were just estimating the energy, let me just send you a low energy state, assuming the quantum PCP conjecture. And what happens is, that seems fine, that seems totally consistent. But If the low energy state was the output of a trivial depth circuit, meaning there's a short, very short circuit that outputted that state, if that was the case, then you can go even lazier, right? Instead of sending you the low energy state, you can just send you the description of the circuit that produces it. But when the prover becomes this lazy, it actually lets the verifier become lazy as well. And the verifier now sends, it doesn't even have to use a quantum computer to understand properties of C. He only uses his classical computer. So if the quantum PCB conjecture is true, and all low energy states are, outputs of trivial depth circuits, in some sense they're like classical, then what we get is that we have a collapse in the complexity hierarchy, the QMA equals NP, which is something that's widely believed to be false. So as a consequence, we get this notion that the quantum PCB conjecture is in tension with this notion that low energy states are the outputs of trivial depth circuits. In some sense, the way you can say this is the quantum PCB conjecture implies that the existence of Hamiltonians with sort of robust entanglement. So this seemingly innocuous statement that's just about complexity theory actually has a fundamental underlying statement about NLTS and robust entanglement. And one way to think about this that sort of resolves this mystery is that this theorem isolates the entanglement complexity from the notion of computation in the quantum PCB conjecture. So we've wanted to really understand the quantum PCB conjecture. It will probably resolve a lot of ideas in quantum complexity theory, but we didn't even know where to start. So we said, let's get rid of the notion of computation and let's just talk about entanglement structure.
Can I ask a couple questions?
Yeah.
So when you talk about multiplicative error,
Mhm.
Does that mean you're going to a finite energy density?
Right.
Has-
So if the Hamiltonian is energy between 0 and n, say, you just wanted the error up to like 1% of n.
It is a
Yeah.
density.
Yeah, exactly. Right.
And then I would have thought that one analog with classical PCB is that you can estimate the energy by checking a finite number of terms in the Hamiltonian, but that's not what you're.
Yes. Yeah.
Is
Actually,
that-
yeah.
Okay.
So in order to tell if the Hamiltonian is satisfied or unsatisfied, so it says that it's hard to tell if a Hamiltonian is frustration free
Mhm.
or very frustrated. Like distinguishing those two situations is hard to tell. Like a priori, that doesn't seem easy. So like what you might say is like, okay, I take one term, okay, it's totally satisfiable. I check another term that's adjacent to, I can find a solution of those guys. But in order to find something which is frustrated, I have to do some sort of big loop. Right? So that seems hard to do. That's what it says. Yeah. Okay. Interest of time, I think I'm gonna not say anything about the proof of the NLTS conjecture, and let me just say stuff about even more on description complexity, because this is sort of what I'm fascinated in. So Noah, you brought up this great point that, hey, NLTS, what you're just talking about circuit depth lower bounds. It's totally reasonable. And that's because I said, hey, well, there's this connection, but I explicitly said it's a connection, didn't say it's any implication or something. It's just some ideas that are connected. What if you wanted to prove lower bounds on the lengths of classical descriptions without making this assumption as to what the description looks like? And so there is something you can say about that, and I wrote a paper about this last fall, which is how do you prove exponential lower bounds for ground state descriptions? So now I'm going to even ease back a little and try to prove very strong lower bounds, but just for ground states. I'm not going to prove them about the low energy states, just for the exact solutions. Let me try to prove that those are really complex. And to do that, I have to introduce another complexity class. So you'll see that there's a deep tie-in from like these complexity classes and actually, physical statements about states, right? So what do we have? We have these two classes which we've already talked about, NP and QMA. What is NP? You send a classical question, you get a classical answer. Prover is classical. Verifier is classical. QMA, you send a classical question, you get a quantum answer. Verifier is quantum, crucially. Intermediate class sits between them, where now the communication is entirely classical. They just send each other letters, but the verifier is allowed to be a quantum device. And you trivially get this double containment that QMA is contained in QMA contains QCMA, which contains NP. But we don't know how to separate them. In fact, any separation that would actually be a very big computer science feat. Why talk about these at all? Well, if you could separate these left two classes, then you would get that ground states do not have polynomial size verifiable classical descriptions. And this is actually just a simple proof by contrapositive that if descriptions existed for ground states, then any QMA prover could become lazy and instead send just the classical description of the state. You could just send the polynomial size description, and the verifier is able to use that. So what we get is that this very question that we wanted to ask about description complexity actually has a notion in computation. Description complexity implies something interesting about computation, so we can take the computational lens to sort of understand it. This is like saying something like, okay, well, it's easier to just send the quantum state, or if you want to describe this, this huge mountain of paper. It's impossible to write down a description of the state. The only way to describe it is just by sending it physically. So how do we prove it? Or how do we make this statement? So, well, we couldn't make it exactly about ground states of local Hamiltonians. If we did that, then we would have done something truly surprising. What we can say is that there's a natural notion of a generalization of local Hamiltonians. So what you can do is you can take this problem where you want to prove something, which is about local Hamiltonians. You can sort of massage it until you've massaged it enough until you can prove lower bounds. The question is, how far from reality did you stretch the question until you were actually able to prove it? So what we show is that there's a distribution testing problem. So that's the setting where the prover and verifier both get access to a distribution. They want to learn some properties of the distribution. And the prover is able to convince the verifier of a property of the distribution when he's able to communicate with him quantumly that he isn't able to do classically. Yeah, question in the back?
Sorry, when you argue from this, like if you assume QMA is separated from CMA, and that this should imply that there's no efficient descriptions of the quantum states you would send on the QMA side. There, the verifier is polynomial, so I guess you again mean some notion of descriptive complexity where it's efficient to unpack the description.
Right.
Then it's surprising that you have two slides from then, you're saying any description, that there's no small description of any kind.
Yeah, exactly. So if QCMA is not equal to QMA, then ground states should have polynomial verifiable classical descriptions, right? Because you could send the verifiable description. So the key word here is verifiable, not just any description.
Okay, I didn't see that.
Yeah.
Okay.
In fact, here, just for the interest of space, this should say sub-exponential size verifiable classical description. Because always, there always existed that tautological answer that we just hate. But because of that tautological answer, implicitly descriptions should always be thought of as verifiable.
Okay.
Yeah. No, great catch. Okay, let's see, 1250. Maybe I can say just a little bit about what this question is. So what we do is we want to generalize the notion of local Hamiltonians, and there's sort of a path. You can keep going. You take local Hamiltonians, they're equivalent to sparse Hamiltonians. Then you add some notions of oracles, and there was a lot of previous constructions, and there's sort of this optimal oracle separation. Okay, but what do I want to say? Where do you want to prove these oracle separations? Whenever you have Hamiltonians that are sparse, so they're mostly zeros, they should always be thought of, in my opinion, as graphs. It's always an underlying graph that sits with it. It's a weighted graph. But you can also turn that on its head and say, I can take a weighted graph and I can always write down a sparse Hamiltonian that corresponds to it. Just flip the problem around. And what you get is that sparse Hamiltonians can actually then encode graph properties. So you could ask about exponential size graphs via sparse Hamiltonians and ask about their properties. And that's what we say, is that there's this problem in QMA, which is deciding if a graph, which is given in this sparse model, if it has many components or is expanding. That problem is in QMA. But you can prove that under some small perturbation that problem is not in QCMA. We give sort of the strongest known separation between these two complexity classes, which suggests that ground states are very hard to describe. Okay, let me skip this for time. Okay, so we're coming up on a sort of an interesting thing, which is that states, understanding their complexity seems fundamentally related not only to computation, but also just, how do we think about them? How do we manipulate them on quantum devices? So we should sort of come up with a complexity theory that is legitimate for the quantum world. And for that, I'd like to make a pitch for a definition of state complexity, analogous to sort of the definitions of complexity theory that already exist. So what should a state complexity class be? Well, you might be familiar with the decision complexity class. Like this is a decision complexity class for QMA. I describe a problem. I just say, hey, does C accept any quantum state? Is it a circuit? Does it have anything that would make it input output 1? Quantum question. You could ask some device and it just tells you a yes or no answer. That device may be quantum, that device may be classical. We can analyze it through a complexity theoretic fashion. Analogously, you could say, let's say there's a state complexity class, which is instead of describing a decision problem, I describe a quantum state. So a reasonable one would be give me the accepting quantum state of C, output the accepting quantum state. And you can imagine an object which then has to output something, right? So of course there's tautological answers. There's also physical answers. It could output the exact quantum state in quantum mechanics, or it could output a description. But underlying it is just very simple notion. There's what we had in decision complexity, we can talk about in state complexity. So let's do an example. You have QMA, which we talked about earlier. You give it a Hamiltonian description, it tells you the ground state, right? You could ask about state QMA, where the prover now tells you, he just tells you an untrusted state. You don't know what it is. Maybe it's the right answer, maybe it's not. The verifier then does some logic with its quantum device to either abort saying whatever it gave me was not the right answer, I don't know what the right answer is, or it outputs some target state. Now the target state could be the untrusted state, it could be something else, we don't know. And you could ask, how does this class state QMA compare to QMA? And one thing you can show is that it's actually easy to prove that state QMA contains the ground states of local Hamiltonians. And you can actually say a little further, you can say morally it exactly equals the set of ground states, up to some sort of notion of approximation. But now if you try to compare this notion of state QMA and QMA, you realize that it's almost intangible. That everything you could say about QMA, you might not exactly be able to say. So you can imagine another system where you have a quantum device, where this device, it now gets to ask an oracle, it gets to understand answers to QMA questions. So you can say, hey, what would the answer to this question be? What would the answer be? A decision question. So it gets to understand decision questions, but it doesn't get to get the solutions, states. It doesn't get states, it just gets to understand answers to what decision questions look like. This would be something called like state distributed QMA. Or another notion, it would be called search to decision. And you can prove, and we proved this last year, that under a notion of oracle separations, you can produce states here that a quantum device with access to sort of just the answers to questions would not be. So it says something fundamental. This looks kind of confusing, but this is the most technically correct way of saying it. Is it says that calculating the ground states of Hamiltonian systems seems harder than calculating the ground energy. Or eigenvectors are harder than eigenvalues, which is classically not the case. Classically, if you can calculate eigenvalues of like NP complete questions, then you can also calculate the corresponding eigenvectors, the solutions. So what we have is sort of something amusing is that, we have the state complexity seems to behave very differently than classical complexity. And there have been a few other results. Let me tell you about one called state QIP equals state P space by Rosenthal, Mecker, and Yuan, which was to understand how does this work when you now have interactive protocols for generating quantum states. And in that setting, they were actually able to prove that the classical equivalence actually yields a quantum state equivalence as well. A big open question in this area is now, not just about state complexity itself, but also about transformations, about the complexity of state transformations or unitary complexity. And the big open question here is the one posed by Aronson of can all unitaries be synthesized with access to a suitably powerful oral? We don't know this, but this seems like a very interesting avenue to open up research. Yeah, Ani?
Sorry, can I just ask you to explain what state BQP is again? I'm given a state and then what?
State. So this is state BQP to the QMA.
Sure. I'm not asking about the oracle. I'm just asking about like state BQP itself. What's the definition of that?
It's just any state that can be produced by a polynomized quantum circuit.
Great.
So it's the state solutions. BQP is a decision class. It's a collection of yes/no questions that are answerable. This is the collection of outputs.
And the same constraints as before, like bounded fan and whatever. It's just
Sure. Yes, whatever you can do in polynomial time with the quantum. Okay, so let me say a little bit about just future questions. So the first obvious future question you should talk about is quantum PCP. Let's not say any more about this other than let's say that the NLTS result about the many body entanglement is just a small sliver of the answer. There's much more to be said about robust many body entanglement, and this computational lens of quantum PCP might be the right way to look at it. Let's see. Okay. Let me skip this about what we could say about stronger lower bounds. If there are questions, I can come back to it. But let me just say that, the real big open question, I think, is just we should really flesh out this notion of state complexity. So we have started to understand, okay, there's these definitions of state BQP, state QMA, but a lot of the magic in classical complexity theory that was so powerful in explaining our understanding of computation was notions of like reductions or hardness of approximation, interaction. And we don't know what those behave like in the quantum state setting. So I'm not making any guarantees, but I would believe that if you were able to understand these sort of notions, it would give us a better understanding of state complexity as a whole. Specifically, something I've been thinking about the last couple of days is sort of what is the nice notion of state NP, or states which you can classically verify, classically describe, which should include sort of these trivial depth states. But how do we generalize them? How do we think about NLTS in the context of state NP? This is something I'm happy to talk about more if there are questions. Okay, I think with that I'll end.
Questions? I guess we go with students first, right? Students have any?
So I'm an experimentalist, so I think I have sort of an experimentalist question for you.
Yeah.
In some of these Rydberg simulators, there are nice possibilities for realizing highly non-local, like not interactions, to potentially make some of those states that you said would require exponentially large data.
Yeah.
So I guess one question is there a nice experimental way to verify that you've done that?
Yeah, so the beautiful thing about the NLTS Hamiltonians is that the statistics are completely known, because the NLTS Hamiltonians we constructed fall into this family called stabilizers. So actually we know all the statistics of them. There's not a computational question involved with them. We actually know just about everything we'd want to know about them by theory. So you can check if you observe the correct statistics, and if you observe the correct statistics, you must have been doing something non-trivial and truly quantum.
So to be clear, what do you mean by, do you mean correlations of all of the bits?
Well, I just mean that if you measure an observable,
What kind of observable do you have?
any local observable, we know exactly what the output distribution should look like. So if you measure a binary observable, we know that it should occur as 1 with probability p and 0 with probability 1 minus p, and then you could just check, hey, did I actually receive those statistics? And if you achieve the statistics predicted, then you know you are a low energy state, even if you achieve them approximately. And the NLTS, this theory provides you the proof that, well, you couldn't have generated this without doing something truly quantum. Like, there's no classical object which can display these statistics, even approximately. So, whatever object you have in front of you is faithfully quantum. In some sense, it's saying that if you trust your measurement apparatus, the physical device.
Do I need to trust it exponentially well?
No, that's the beautiful thing. You only need to test it to like constant precision, right? That's what because you're proving something about all states of energy less than epsilon n.
Do I need to detect like an exponential number of observables?
No, just a constant number. Right? I mean, all these constant epsilons, these are all.
Sorry, what do you mean constant number of observables?
Well, so you want to. What we have is that if the state if whatever object in front of you has energy less than epsilon n, then it couldn't have been generated by a trivial depth circuit, which means that it's far from a product system. It's far from a classical system, right? In this specific metric of circuit complexity, but it's far from it in other metrics as well. So what you get is that if you can verify that it's a low energy state of the system, and that can just come from measuring the Hamiltonian terms and just checking, right? Then whatever solution you have in front of you must be.
When you say measure the Hamiltonian terms, you mean measure the energy of the state.
Mhm.
And if it's less than some amount.
Right.
Then we know that there are non-local interactions.
The beautiful part is that the Hamiltonian itself, if you do it right, it's frustration free. So even measuring the Hamiltonian term should not perturb the state in front of you. So you can measure as many as you like in any order. Yeah.
Kind of a related question. So in these NLTS Hamiltonians you define, are the Hamiltonians, is there any notion of geometric locality in them? And if not, is there any hope of making a geometrically local version of NLTS?
Okay, so no, they aren't. The geometry, if you're curious, is like a 4D hyperbolic surface. In this case, it's not.
Yeah,
not
so
Euclidean, but
is there any hope of proving like say a 2D local version of
Right.
of NLTS, or is something like that?
So you can prove in the 2D setting that all states of energy less than n to the 0.99 times some constant have high circuit complexity.
So not constant times that.
Not constant. Okay. Right, and that seems to be tight in that setting. Yeah, you can.
Oh,
prove.
so you think that a 2D geometrically local version of NLTS, you think that that's actually false then?
Yeah.
Oh,
It is false. I know it's
it is
false.
false. Oh, interesting.
But that's because the notion of every low energy state that's hitting from like the computer science adversary providing a deceitful notion. It's not the notion of approximation that you might encounter from a physics perspective, which is like a more natural, you let the system evolve with time and it sort of moves a little bit outside the exact ground solution to a low energy solution. That's a much smaller class of low energy states. Right? You can prove something about maybe those, but maybe not about these like adversarial low energy solutions in 2D. So that's worth doing. I think it will involve some new techniques, which
Of course, the adversarial model can still make sense in the experimental context because it's like if the whole point of this is to try to test that your device is indeed working and integrated the way.
Yeah, like my understanding is if someone shakes the table, it might have a big energy jump to some other low energy system that might not have had a continuous path. So.
All right. Well, thank you very much.
Thank
for
you.
the